Hello, Bruce. What I'm going to show you here is an example of a program I've been working on for a number of years. It started out as a simple computerized version of flashcards, and it's grown into something else. So I'm going to illustrate the program by discussing the concept of thrust, the thrust of a rocket. I figure you being a rocket man will have some familiarity with the topic, and therefore this might make some sense to you. What I'm going to say has been inspired by a lecture by Walter Lewin on YouTube. He's a professor at MIT, and this is his introductory lecture on physics, and it's lecture 17. So if you want to see how he handles material, you should check this out. He really does a nice job. His experiments in front of the class are just excellent and really help you understand the stuff. So if you go to YouTube and type in Lewin 801 Lec 17, that should bring up this lecture 17, where he discusses, among other things, the thrust of a rocket. Now what we're going to do is, first of all, we're going to go down here and look at a rocket simulation, which in some sense is the end point of the discussion, but it's also gives us a nice platform for introducing all the concepts we'll be interested in. Then we're going to go back up here and talk about impulse. Impulse relates force, momentum, and time. This is sort of a remedial module to just review some physics that probably you haven't looked at in some time. Then we're going to get into the heart of the matter, which is here, and it's a discussion of how the velocity of a rocket changes in relation to the fuel consumption, and it introduces the concept of thrust. And then finally I'm going to look at the thrust quiz. I am a fan of rote memorization, and that's all the thrust quiz is. It's just a way of familiarizing yourself with the concept. It's sort of the flashcard concept that I started out with when I developed this program. Now I'm going to show each of these modules in separate videos so that you can look at one or the other according to what you are most interested in. So eventually you probably want to review this one here several times, because that's the meat of the argument right there. And the others you can look at once and get the big idea. So, but I'm going to start with a rocket simulation. I'm going to do that all in this introduction just to get the concepts on the board. So let's go to the rocket simulation, and let me initialize it and clear my temporary marks, and let's just fire our engine off. And what we see is the rocket taking off, and we see the exhaust of the rocket is shooting out the rocket engine at a certain velocity. The engine cuts off, and momentum carries the rocket upward further, but gravity is always pulling it down. Eventually gravity slows the momentum to zero, and then starts increasing the momentum in the negative direction until the rocket crashes back onto Earth. So the things that are important there, or the things that we're going to be focusing on, let me stop that, are the rocket itself and the exhaust. Those are the two things that we're going to have to pay attention to. And the concepts that we're interested in are, first of all, the force on the rocket. What is the force on the rocket? The two elements to the force. One is the thrust of the rocket engine, and the other is the force of gravity. So the rocket engine is propelling it up, and gravity is propelling it down. M here stands for the mass of the rocket plus the fuel at some point in time. Now, since the fuel is being burnt, this sum of metal plus fuel is changing, and that's what the mass is. So the mass is a function of time. And let's go up here to our diagram and go over some of the terminology that we'll be using. So we're going to be looking at the rocket at some arbitrary point in time, and at that point in time it's going to have a mass m, which again is made up of steel in the rocket, steel and plastic and maybe even the astronaut, and the fuel. The fuel is being burnt, so that m is changing over time. It's decreasing as the fuel is burnt. And some more terminology. Our VI will stand for initial velocity at the beginning of our interval of time, and MI will stand for our initial mass. Now, after some period of time, a small interval of time, which we'll call dt, the picture has changed. Our mass of the rocket has gone down. Our mass of the rocket fuel complex has gone down because we've burned some fuel. And this absolute value of dm, that's what the little bars stand for, absolute value. We need to put those in because dm is a negative number. The mass is going down. So if we want to express just the quantity of mass that is burnt, we have to put the absolute value sign around just to turn it into a positive number. So nothing very deep about that. So after a certain amount of time, the momentum picture is a little more complicated. Over here on this side, it's just m times v is the momentum. On this side, you have two pieces to contend with. You have the m minus dm combined with the v plus dv, because remember the rocket velocity has changed a little bit due to the propulsive power of the engine. So that's one element of the momentum. But another element of the momentum is the exhaust, which has mass dm and has velocity u relative to the rocket. So when we do our mathematical analysis in the next module, we're going to have to pay attention to all those pieces. Right now, though, let's just get back to sort of our overview. Let's go back to thrust. What is the thrust? Well, the thrust is, let's say, is defined. It's not really defined. We're going to derive this formula in the next module. We'll show that the thrust is the product of the burn rate times the velocity at which the exhaust is being propelled from the rocket. And we're going to do that by starting out with the showing that the conservation of momentum principle leads to this definition of thrust. So it's not really a definition, it's a derived equation. The thrust is the product of these two things because momentum is conserved. All right, a bit of an interruption there, but let me see if I can recall where I was. We were discussing the thrust, and we're going to show that that the thrust is the product of the burn rate and the propulsive velocity. And it sort of makes sense, even without any kind of derivation, that the power of the rocket should depend on how fast you're burning fuel, which is the burn rate, and how fast that exhaust is being propelled out of the rocket nozzle. So it certainly makes sense. Now, what do we want to talk about next? Alright, let's go up here and look at our inputs. The pink numbers are my inputs. I get to put those in, and in my little toy example I can make them anything I want. And the blue numbers are either calculated using a formula that we'll derive in the next module, or they're being calculated using the simulation. And just to put a little real-world flavor in this, according to Walter Lewin, the burn rate of the Saturn rocket was 15,000 kilograms per second. So that's the Saturn rocket, 15,000 kilograms per second. And the u, or the velocity at which the exhaust was being propelled, was 2,500 meters per second. So if you plug those numbers into our formula for thrust, you get this as the actual thrust, and that's in newtons. So it's 37,500,000 newtons of thrust propel the Saturn rocket upward. Now Walter doesn't tell us what the weight is, so we don't know what the net force up was, but it's probably a pretty big number. Now let's go back to our toy numbers, and I want to just play with this a bit just to cement these ideas. So what I have here, I had 50 as my burn rate, and I had 100 as my propulsion rate. Let's look at what that means in terms of our toy example. So I'm going to pull up my calculator, and here are the numbers. We have the thrust, which is the burn rate times U, is 5,000 newtons, and we compare that to the initial weight of the rocket and fuel of 1,960 newtons. So we have way more thrust than weight, so the rocket will take off. Now remember, the mass of the rocket fuel complex is changing over time, so its final weight is 1,666 newtons. Let's do a little experiment here. Let's go over here to our burn rate and make our burn rate 1,960 divided by U. If we do that, our thrust is equal to our initial velocity. So the question is, what's going to happen to the rocket? Will it lift off the ground? You might think not, because its weight is equal to its thrust. But let's go over here and see what happens. So I initialize, first I got to initialize it. Then I start my engine. And it is actually taking off ever so slowly, but you can see the velocity changing, and there it is lifting off the ground. So why is it lifting off the ground given that the weight and the thrust are the same? Well, the reason is the weight is decreasing as the fuel is used up. So eventually the thrust becomes greater than the weight, and it does take off ever so slightly. If I wanted to kill it completely, I could make my burn rate equal to the final weight, which is 1,666 divided by U. Okay, now if I look at compare my thrust, which is this number here, with my two weights, it's not bigger than either of them, so it's not going to take off in this case. So let's just check that. So let's initialize thing and then start my engine, and it just sits there, never takes off. So everything sort of makes sense, and I think that's all I want to say about in the way of introductory remarks. So let's go on to the next module. I'll close out this module, and we'll go on to the next module, which will be just a short discussion of the notion of impulse.